Well, good day, everyone. Welcome to another Sunday Toolbox Tech Talk with me, Glenn Morris from the Smart Energy Lab. Great to have you all here. I can see people turning up on the different platforms. So we're live to YouTube, Facebook groups, Periscope, which is part of Twitter, so you should be able to see it there. And very soon LinkedIn, once they get their response to my request to be able to stream to them. So basically all sorts of platforms you can watch this. And everything today is, of course, recorded, and you can watch it if you miss any of it. So what are we going to talk about today? Well, I kind of pitched this as... Let's get technical. Kind of reminds me of a song. No, I'm not going to sing it. Too daggy. But anyway, we're going to talk about solar and batteries, and I think I should just get my sunnies off. I can't even see with those on, but it's part of the promo, isn't it? Anyway, so what we are looking at today is these are the topics for today is solar and batteries. So we're going to look at AC and DC coupling first. So we're going to take it slow, a little bit of basic explanation about how it all works. Then we're moving on to some compliance and looking at the different compliance requirements for batteries in terms of the battery standard 5139, ASNZS 5139, and compliance covering sections 4, 5 and 6. Generally a bit of an overview. Then we're going to burrow down into 2 case studies to make it real. We're going to look at a Section 6 system. Now that was a request from one of the audience actually before today started. And then we're going to do a Section 5 case study, which is an on-grid. So we're doing an off-grid system and an on-grid system configured as a Section 6 for off-grid and a Section 5 for on-grid. And then we're going to talk about location, which is the big deal with the battery standard. Where can you install a battery? It's really a major issue these days. I'd like to start off with just asking people to post comments in the chat. So if you've got any questions, observations, whatever, just post them in the chat there for me, and I'll read them and respond. So feel free to just do live chat with me, and I'll answer those as I can. So let's just have a look at the topic number 1, which is about why would you choose solar and batteries? I mean, the basic premise here is that there must be some benefit for having solar and batteries. People wouldn't want to buy them. We've seen solar incredibly popular in Australia. In fact, we have the highest per capita in the world uptake of solar panels for residential use. So something like 2.2 million homes, so last count, have solar installed. And that's been driven by government incentive schemes, but actually price of installations and solar panels have come down so much that it's an extremely affordable choice. And of course, compared to paying for grid power, it's now almost straight away a more sensible choice if you have a suitable roof. Why batteries? Now, batteries have come along in on-grid only recently, but off-grid they've been there for over 40 years. So for those who are used to working in the off-grid environment, there's nothing new about batteries, because how else are you going to store the solar energy? So why batteries on-grid? To some extent, we're driven by the enthusiasm for new technology, and so people are buying batteries, even though the economics probably don't add up yet. Though we're getting very close to it, and if you're just looking at batteries as purely a means of shifting energy that's generated during the day to use it at nighttime, then which is called self-use or load shift or generation shifting. It's probably marginal in terms of the payback period. If you look at the warranty of a product, it might be, say, 10 years. Will it actually pay for itself in avoided grid costs? I'd like to give a little plug to solarquotes.com.au here. Solar Quotes, actually run by Finn Peacock and his team, do a great job of doing an assessment on different products in terms of the cost analysis. And he's got on his website some comparative tables of payback or simple payback calculations for different battery systems. So that's solarquotes.com.au. He's not a sponsor. I just know him as a friend, and I think he does a great service for the industry. So batteries for self-use, marginal in terms of the economics, but getting there, and it's probably only a matter of time before it's just the sensible choice. But when it comes to things like other services that batteries offer you, the ability to operate when there's a grid failure. That's a big one. So Australians are very fond of the idea of independence, and having that backup capability is a big driver for battery storage systems on grid. What's interesting is it's not the norm in all parts of the world. Our market's a little bit backup centric. So quite a lot of products that come to Australia and here at my lab, I often say, and what's the backup rating of that hybrid inverter with batteries? And they go, oh, no, it's just self-use. You don't really need backup in Australia because you've got a reliable grid. So yeah, that's not always the case. I'm just keeping my eye on the chat here at the moment, see if anyone's got any questions for me. Can't see any right now. Just keeping a little side eye on my Facebook feed and my YouTube chat. Okay, nothing there yet. And I'm just looking around to make sure all the feeds are running. Yep, they are. And so I've got, oh yeah, quite a good little audience there on Facebook. It's nice to see you all guys. So coming back to some more technical stuff, I'm going to draw stuff today. I'm going to explain stuff because today is Let's Get Technical, and I don't have any guests today. It's just me. So I'm going to do what I really enjoy doing, which is explaining stuff with drawings. Somehow it sort of makes different people approach learning in different ways. Some people are good at just listening to someone talk about something. Others are better when they can do it with their hands, and others when they see it done. So I'm trying to cover off on all those different skills, although you won't be doing any solar installation with me here on the live stream. But I do actually run training courses here at the Smart Energy Lab, and at the moment I'm running them as a virtual course. So for those of you who can't attend my face-to-face courses, I'm not running them at the moment because of the lockdown and the various restrictions on travel. I do run online training courses. It's a 5-day course, half a day, every day for a week. I just finished my first one last week, had 10 students on it. That was great. And I've got another one coming up next week, the 5th to the 9th of October. So if you're interested, the description of that course is in the YouTube comments. Anyway, back to AC and DC coupling. Now, let's kind of give you a very simple explanation of that before we start going down a little bit deeper into the standard. And so I'm going to switch over to my drawing tablet. Oh, it's actually a pen and paper, believe it or not. So let's just see if that's going to work. Here we go. That's my piece of paper. And I'm just going to bring myself up in the corner there so you can see me. Okay, good. So AC and DC coupling, what's that all about? Well, I'm going to sort of a line down the middle. I'm going to do AC coupling and DC coupling and keep it sort of simple. So let's just imagine we've got a grid, it's a power pole, and the power's coming into your home. In your switchboard, you'll have some circuits running off that main switchboard or subboard, and you may have an existing solar installation. And this is the symbol for an inverter. It converts AC to DC, and you've got some solar panels connected to that. So here's our little solar array. Now you've already got this, so we're going to call this a retrofit solution. The customer already has solar, and they already have solar that's exporting to the grid when they're not using it themselves. So here we've got the loads in our home. Okay, so that's our basic installation of a Grid Connect system. So let's say we've got a 5 kilowatt inverter here, and we've got a meter. That's actually quite important. So there's a meter here, and this is the utility meter, or more technically, the meter installed by the Distributed Network Service Provider, DNSP. That's their meter. So that's what you get billed for. Now, the solar system, of course, is producing electricity when the sun shines, and predominantly supplying your loads, and then any excess may flow to the grid depending on what your application approval has been for. But you might want to add storage. Now, this is where this coupling comes in. How do we add storage? Well, one of the simplest ways, and we call it AC coupling. Here we go, AC coupling. Is to add another system, but it's another inverter basically, that has a battery connected to it rather than solar panels. So here we go. This is a battery inverter. Now the symbol for a battery, that's a cell, that's a lot of cells. Let's just call that a battery. So that's our battery here. and that's our solar panels there. Now, how does the energy get from one place to another? So this part here is DC. The DC energy from a solar panel, how does it get to the DC battery? It gets to it through the AC grid. It gets to it this way. So that's what the coupling's about. How does the energy transfer from your DC generation to your DC storage? It's through the AC grid. But one of the advantages of this is you might notice that we had this already and we could add this later on. It didn't actually have to be installed at the same time. So that's a big plus. We could actually have multiple PV systems and multiple battery storage systems too, so they can scale up to the limits of your approval from your electricity distributor, of course, because they'll put limits on how many the inverter capacity that you can connect. Having drawn it like this, it won't work. And you might go, Glenn, hang on, why did you even bother drawing it? It won't work until we put in one other component, and that is the energy meter. Now, the energy meter is supplied with the storage inverter, so I'm going to put it here and call it EM, energy meter. And so it's an additional meter. It's not the DNSP's meter. It's not the one that you pay your power bills on. But this energy meter allows the installation to see which way the energy is flowing. Is it flowing out, or is it flowing in? So it's actually a measurement device to look for opportunity. And the opportunity is being communicated through to your battery inverter. So there's a comms link, communication cable, that goes through to your battery inverter, and it tells the battery inverter, is there an opportunity to charge from free renewables? Or is there an opportunity to displace expensive grid power with stored energy? So a battery inverter is a bidirectional device. So this system can import or export power, and so it can choose whether to support the loads or to import energy when the solar is generating and charge its battery. And of course it can do that in any combination. So it can be partially exporting to the grid, partially charging batteries, etc. That's AC coupling in a nutshell. Now, DC coupling historically was the only way of charging a battery. So I might kind of draw DC coupling in two modes actually, and one of them would be more common in off-grid now, and the other more common in on-grid. So DC coupling. Now, I'm going to draw a grid symbol here. There's my power pole, and I'm running power to a house, and the house has let's draw it over here. It has an inverter, and this inverter is connected to a battery. So far, so good. And we've got some loads in the home as well. So that's our loads here. But this battery inverter also has solar connected to it. So the solar is connected onto the battery terminals, basically, or within the inverter there'll be what's known as a DC bus, and it will connect in there as well, possibly. So it depends on whether the configuration of the system, whether it's an external connection or not. Now, this might be pretty basic stuff for installers. Don't worry, we're getting through to the more technical stuff, but I'm just ramping it in there a little bit, not going too fast, too quickly. So this is a DC coupled system, and the reason it's called DC coupling is that the DC energy gets into the battery directly. It doesn't actually have to go through an AC network. Equally, this system needs that energy meter as well. The reason is that this battery system here doesn't know that you're using any power, so it doesn't know to support the loads. And so we need our energy meter supplied with the battery inverter system here that communicates with your battery inverter and tells it when to charge and discharge to support the loads, or you can even do some clever things such as what they call time of use charging, which is where you're allowing the battery to be charged from the grid as opposed from solar. Not all products have this capability, but if you've got a big price differential between off-peak and peak, you may actually choose to use some grid power to charge your batteries. All right, I'm just checking to see if I've got any questions so far. So in YouTube land, I don't see any coming up on my YouTube feed. So there's no questions there. Now, I just noticed my Facebook comments haven't started playing. So I'm just going to reload that page there. There we go. And, oh, great. We've got some comments. Fantastic. Thank you, everyone. Sorry, I didn't see those straight away. So at the top of the list, it's probably the reverse order actually, is James. He's asking about, we have a 1380 amp hour 24 volt flooded lead acid battery bank, which is 8.5 years old. And I'm wondering how to determine how much life they have in them and the state of health rather than the state of charge. Is there a formula for doing a load test to an end voltage? And the question goes on. It's a good one actually, and I will get to this. It goes on, is there a load test like an end of voltage at a certain discharge rate to determine remaining capacity, or is there a service available to do a report on the state of health of a battery bank by performing other tests? Don't want to overinvest in 24 volt, as if we were to buy a battery bank in the near future, it would more likely be 48. So that's a pretty common scenario. It sounds, James, like you're probably off-grid if it's quite a large lead-acid battery bank, and flooded batteries are pretty rare these days. You can still buy them, but they're not very popular because of just handling. There are other nasty things to have to transport. But they do work. If I was to be honest, I'd probably say that a flooded lead acid battery, well maintained and well looked after, will be one of the longest lasting batteries you can still get. But the problem is maintenance. They really need a lot of tender loving care. You've got to make sure that distilled water is added to them. It's not contaminated. That you keep the terminals clean. That you make sure you do an absorption charge at the recommended intervals, that a certain amount of gassing has to occur to stir up the electrolytes so that it doesn't stratify, all of these things, and that you keep them in a fairly stable temperature throughout the whole bank, not one end hot, one end cold. All these things are not trivial, but if you do them properly, they will last a long time. I've actually replaced some lead acid batteries here at the co-op where I live, which were 27 years old and still working. Kind of, just, but they were still in there. It's amazing how long they can last. And the other good thing about a lead acid battery is it's actually a positive end of life cost. You'll get paid quite a bit of money for those batteries just as lead. So it's not like it's a waste product that you have to throw in the bin. You can actually get it recycled, or someone will do it for you and pay you the money. So to come to your question, and this is pretty common when people have got old batteries, and it's particularly lead acid, is how do we ascertain their condition? Really, lead acid battery analysis is a bit of a black art. I often think I feel more like a vet than someone who's working in electrical products to understand the complexity of how to assess a lead acid battery. But there's a few things you can do. Simple one, James, and being a 24 volt system, you don't actually have to be a licensed electrician to do this. You can get a multimeter and test the voltage of all the cells. Now, you would not do that with no load, so you want to turn off your charging sources and turn off your inverter and test the voltage and write it down. So because they're 2 volt cells, you're going to need a multimeter that does at least 1, preferably 2 decimal places. And so you want to know if it's 2.15, 2.10, 2.20, etc. Write down all the cell voltages. It's a good idea to let the battery stabilize before you do this too. So once you turn off all the loads, wait a few minutes, maybe 5 minutes or so, and then do the test. A good check that nothing's changed is actually measure the total battery voltage first. So let's say it comes out at 26 volts. Test all the individuals, add them up, and they should come to the number you first started with. That's what you're looking for there is a weak cell or cells, one with a distinctly lower voltage. Another useful thing, and it's one of the advantages of a lead acid battery, is you can use a hydrometer. Hydrometer measures specific gravity, and so you can record the specific gravity of the cells and look for any that are significantly different. So in terms of voltage, you want to be within about 5% of each other, plus or minus 5%, sorry. In terms of specific gravity, similar, but these things are best done as a long-term observation, so not just one test and write them off. You may be able to resuscitate them, for instance. It might be winter time, like, well, we're just coming out of winter, and your batteries have been struggling a bit because they haven't been fully charged regularly. So you may need to do a couple of absorption charges to smooth out the batteries to find out. There's actually a lot I could say, James, about this, but those are the basic ones you can do. The other ones, if you've got someone who's got some impedance measuring equipment for batteries, now this is pretty expensive equipment, several $1,000s, they can test the internal resistance of each cell. And that's a very good indicator of the health of a cell. As a lead-acid battery ages, its internal resistance increases, and you can look for big differences in internal resistance and see there's a weak cell. You can also get a sense of how much life's left in the batteries, because as the internal resistance goes up, so your capacity goes down and your charge and discharge rate goes down. So there you go, James. That's a bit of an overview. Looking at the questions here, what else we got? Got a few hellos. Thank you. Amerique asks, AC coupling, is any communication run through from inverter to battery or just energy meter? Will only need for communication. Thanks. Okay, I'm a little bit confused by that question. The communication between an energy meter and the inverter, it's not actually the battery so much, it's the inverter which controls the battery, is usually a proprietary communication. It's something which the inverter manufacturer will supply with their product when they sell you the battery inverter. They've come with different names. I mean, for instance, if you're familiar with Tesla, they have a product which comes with the Tesla Powerwall, which is their gateway device. Some companies refer to their device as an energy meter or by model or brand. And some of them actually give you the opportunity to choose your own energy meters. But they're all basically doing one thing, measuring the flow of energy. Some do it simply with what's known as CTs, current transformers, which is just a clamp around a conductor. Some do it by measuring whole of current and voltage as well, and that gives a much more accurate view of energy or power. So AC coupling, yes, you need that meter. And James says, yes, he's off grid. So just making sure I haven't missed any questions there. Wow. Okay. So we've got quite a few people on the Facebook group. I'm just looking over here at my YouTube people and see if there's any questions over there. Just reloading that. So I can't see any questions on YouTube yet. Nope. Okay. Great. Looks like Facebook's the #1 place to be. Okay. Oh, there's some more comments come in. All right, here we go. Jules, certainly piqued my interest. Norm would like to know a little more. So he's referring to someone who's discussing something further down. Oh, there we've got Craig. G'day, Craig. How does cost price compare to other PV hot water systems? All right, so we've got a little side discussion going on here, which actually probably relates better to the live event I did last week, which actually was a little bit later in the day, 4 o'clock, with Gerhard Rimpler and Norm Anderson. So Gerhard from MyPV and Norm from Energy Smart Water. Now, they're in the chat, and so they can probably answer those questions for me. I don't think I need to do it here. And they'll probably point you towards the fact that they've got a Zoom coming up shortly about their product. So they make a product for diverting, I should say MyPV make a product for diverting surplus solar energy into resistive elements, whether it be hot water or a heater or a hydronic system. I've got several here. In fact, that's how I heat my water. So yeah, it's a really interesting product and very, very nice monitoring as well. So, whoa, what a lot of chat about hot water already. Actually, to be honest, a lot of people think batteries are where energy storage starts, but actually energy storage probably starts with hot water because it's the cheapest way of storing energy. There's lots of ways of storing energy. Pumping water up a hill and storing in a tank is stored energy if you need pressurized water. If you need a service every day, like a shower and wash your dishes in hot water, that service can be provided at different times in terms of the heating of that water, and that's why a water tank effectively is a storage device of energy. And so if you can put electrical energy into a hot water tank by converting it using diverters, etc., that's a great way of storing energy. So in a way, if you think about typical usage of a residential hot water service, electric element is around about 10 to 15 kilowatt hours per day. That's a 10 to 15 kilowatt hour battery that you've already got sitting on the outside of your house, and it's perfectly safe and easy to use with an additional piece of equipment. But today we are more focusing on chemical batteries, so I'm just going to veer back onto chemical batteries and talk a bit more about those. So I did a quick explainer on AC and DC coupling, so I'm just cut over to that. So that's the AC and DC coupling that I was talking about. Welcome to anyone who's just joined us. Please feel free to put some more questions in the chat. You're going hot. That's great. But there's one more thing with DC coupling. Now, this style of DC coupling here makes it look like I've got a direct connection from my solar panels to my batteries. But I've actually oversimplified it. I'm just going to cut over and flesh this out a bit more. So you can't just feed solar straight into a battery efficiently or even safely. And so what goes in place in this position here is something that converts from DC to DC. So referred to as a maximum power point tracker. So a maximum power point tracker's job is twofold. One is to operate the PV array at its most efficient voltage and current, and that's what maximum power point tracking is. And the other is to match the voltage of the battery to the voltage of the array. So this array might be operating at, say 150 volts DC, but the battery might be 48 volts DC. And so the MPPT does that voltage transformation. It magnifies the current and reduces the voltage, and it does it at a very high efficiency. So that's DC coupling, where you've got two discrete devices. But a more common mode of DC coupling for systems on grid is where you have one device that does all of this. And that's sometimes referred to as a hybrid inverter. So here we go, hybrid inverter. Now the terminology is a little bit Australian-centric, but because it really just means it's a bit of several things. It's a bit of a grid connect inverter, it's a bit of a battery inverter, and it's a hybrid of the two. So we're bringing our power in. So we've got some loads in the house here. So house loads, light and power, etc. We've got a all-in-one inverter. Now, this is the hybrid inverter that actually has the MPPT and a power and conversion phase built in. So we can connect batteries to it, we can connect PV to it, and it does all of that in one box. Now, one of the big advantages of a hybrid inverter is you're only buying one product. It's also only one inverter. You're not having to have multiple inverters like you may have to in an AC coupled system. And that can be important where you've got inverter limits applied to you by your electricity distributor. The other thing is that sometimes the battery over here is optional. So you can actually start with an inverter that's purely a solar inverter, but it's battery ready. And the batteries, I'm just going to cover them up. The batteries can come along later. So you don't have to commit to buying the battery straight up. But I'd be cautious about making that claim too far into the future, because batteries change, and also inverter communication protocols change. And so if you left it too long, you may find that the battery that's compatible with this hybrid inverter is no longer available, or the communication protocols change and the new models don't talk to the older batteries. So just be cautious about offering that as a long-term upgrade option. It's probably a short-term upgrade option. So that's hybrid inverter, which is effectively DC coupled. Another side benefit of DC coupling, whether it's the off-grid style with the separate MPPT or the on-grid hybrid style, is that it's a dedicated way of charging those batteries. You can charge those batteries even when the grid's not present. So it will look after that battery system independently of any grid source. Okay, just going back to checking on the questions here. Okay. Thank you, Joe. So Joe says, so in short, the pole should be capable to break the full voltage of the array. Okay, all right. We're getting onto some definitely more technical stuff here. So I think Joe's talking about switching of DC. Wow. Thanks, Bradley. You're in there too, helping out. Thanks. That's great. A lot of discussion around MPPTs. I can see that. And isolation. We will get onto isolation and earth faults in a minute, so just hold your fire there. So I want to talk a bit about compliance in terms of the battery standard. Now, the battery standard AS/NZS 5139, I've actually got my little well-thumbed copy here. Incidentally, I'm actually on the committee that wrote this, so I'm pretty much across it. It's relatively new. It was published last year. It came into force in Australia in all states around middle of this year, and New Zealand has kind of got a transitional adoption. It's a little bit more complicated in New Zealand. It's more or less best practice recommendation. So yeah, that's the new battery standard. It replaces the old 20-plus-year-old standard AS/NZS 5139. So yeah, it's really come a long way, and AS/NZS 5139.
Whoa.
So sorry, I just pressed the wrong button then. Trying to look at my comments coming in. So yeah, it's replaced the old standard 4086. And it now provides us with a lot better guidance on installing safely battery systems. But one of the key things people have to get their head around, particularly installers and designers, is the different sections within this standard. There are 3 categorizations of battery types into what we call sections for a BESS, a battery system, and other. And I'm just going to explain those real quick. So when I refer to a BESS, you know what I'm talking about. So once again, I'm just going to jump over to my little drawing tablet here. Bring that up. Okay, so 3 sections, 4, 5, and 6. Now, the reason for those numbers, those 3 sections, is to kind of make life a little bit easier for installers. So if they know what type of system, what type of battery system they're installing, they can straight away look at the relevant section and ignore the others. So it's a bit repetitive. If you read section 4 and then you read section 5, it's almost the same with just a few minor differences. And that's because we didn't want you to have to be jumping all around the standard to comply. So section 4 systems is for pre-assembled battery energy storage systems. Now, the key thing here, pre-assembled, basically means that there's no on-site manufacture. All of the components are supplied, and it may involve, putting together those components, a bit like an IKEA table, but you don't have to go down to the hardware store and get your own screws. Everything is supplied, so you can't make up any cables, select any lugs, and everything must be part of that system. It also is tested to various standards, but it's a pre-assembled battery energy storage system. So that's where the acronym BESS comes from, Battery Energy Storage System. Easy to think of this as an all-in-one. So if I was to draw an inverter, and technically we refer to those as PCE, power conditioning equipment, and we draw a battery, and then I put a box around that. It doesn't literally have to be a box, but I basically put around a pre-assembled solution that is encompassed by that blue line. That is a BESS. But it also has one other condition. It has to comply with a sort of quasi-product standard called the Best Practice Guide for short. It's a collection of documents of international test requirements for lithium-ion batteries, and that Best Practice Guide, short Best Practice Guide, BPG, is also required. So compliance with the Best Practice Guide. So you have to be pre-assembled, you've got the inverter and the battery all as one, therefore it's actually an AC output device, so the output of this system is only AC. You don't have any DC terminals that you have to connect to, and it's a Section 4 solution. Products like Sonnen battery, Tesla, Varta, these are some of the examples of an all-in-one BESS, battery energy storage system. Next, we've got a pre-assembled battery system. It sounds awfully similar. So, pre-assembled battery system. So now we're just talking about a battery, and it may include some battery management as well. So we've got what we could call as a battery management system and a battery. Incidentally, the pre-assembled BESS also has a battery management system as part of it, but I haven't bothered drawing it as a separate entity. And now I'm drawing a box around this and calling this a pre-assembled battery system. So as you can see, the output, there's no inverter drawn in this picture, so the output is DC. So it's DC. And it also requires compliance to the best practice guide. So plus best practice guide. And if you're wondering about this best practice guide, that's something the manufacturer has to deal with, that compliance. It's a self-certification, though the Clean Energy Council have a list of approved products that they feel have met that requirement. So you can often check on the Clean Energy Council's approved products list for battery systems and BESSes that have met the best practice guide requirements. So that's Section 4, Section 5, Section 6. What's Section 6 about? Everything else. Section 6 could actually be these two things that don't comply with the best practice guide or haven't got declaration of compliance to it. So Section 6 is kind of a catch-all for things that are deemed to be sort of possibly higher risk. They're not necessarily higher risk. In fact, they may be the safest battery in the world. If someone invented a water battery that ran on water, it would be in Section 6. The irony is there's no opportunity for non-lithium ion batteries to be assessed in Sections 4 and 5. And incidentally, compliance goes upwards, more difficult. So 4 is the easiest, 5 is a bit harder, 6 is harder again. So 6 basically is everything else. All right. And as I said, it could even be very safe batteries fall into Section 6. But it does mean there's more complexity, because chances are it will be a range of components that are put together as part of a design. They may not be from the same manufacturer. They may be deemed to be compliant with each other by various manufacturers, and the installer puts it all together and makes it work. But that's a higher risk than something that is assembled or designed, made in a factory, all the components are supplied, and it's tested. That's the key thing, and it's tested to be safe. Whereas here it's really self-assessment on terms of risk. So that's Sections 4, 5 and 6. So just going back to look at my questions, see how we go in there. And unfortunately with Facebook, I've got to keep reloading the page. So for some reason, it's not streaming the questions. And I don't seem to be getting my YouTube questions coming through. Not sure what's going on there. View, reload this page. All right, so just looking through the questions coming up here. It's good if you have a question directly for me, you say, Glenn, that's great. Because I see there's been quite a lot of chat between people in the comments. So Lewis asks, hi Glenn, is it required to isolate all 3 actives as well as neutral from the grid when a battery backup mode kicks in if a single-phase PV and battery system is installed on a 3-phase power supplied home? Okay, so some of this actually applies to, is covered by AS3000 in terms of what levels of isolation you're required to have. AS3000 has a clause in it that states that there must be continuity of the neutral conductor to the MEN, so you're not supposed to be interrupting that neutral conductor with a switch, so that the neutral conductor should be continuous. Though I am somewhat confused where some products do this and seem to be on the approved list. So I don't quite understand how that can happen. But anyway, I'd suggest that you be very careful with any neutral interruptions, and that should be confirmed as being compliant with AS3000 beforehand. NZS 3000, sorry for Kiwis listening in. Sean says, Glenn, have you had any experience with lead crystal as neutral from the grid when a battery backup mode kicks in? Sorry, I haven't had any experience with lead crystal, sorry. I've got a lot of chemistries here. That's one I haven't got. I've got a lot of different lithiums, flooded and sealed lead acid, advanced lead acid, molten salt batteries, zinc bromine batteries. Yeah, there's a lot of different chemistries out there. Sean says, I have 4 120 amp hour that I want to hook up to my SunGrow hybrid inverter for redundancy in case of a blackout. Is there anything specific I should be looking for in these batteries? So it sounds like you've already got the batteries, Sean. Different inverters have different program settings. Some will suit a particular chemistry, even a particular brand and model of battery. So in the case of SunGrow, if you're talking about the SunGrow hybrid, they do actually have a lead acid profile in there. So yeah, I imagine that lead crystal may just be a tweaking of some of those charge settings in terms of maximum voltage and minimum voltage. But some inverters are not very suited to other chemistries. They might be really wedded as a managed battery, one that has a particular communication protocol. So I guess my advice to you, Sean, is just check with SunGrow. I don't want to tell you something that's not true. Idris, hi Glenn, can you please talk a bit about risk assessment forms and control for the lithium-ion battery? Yeah, risk assessment is actually a big part now of the battery standard. It's a whole appendix in 5139. There's a sample risk assessment. Incidentally, the Clean Energy Council have produced a document called the CEC Advice on ASNZS 5139. Just pointing out it is advice. They actually are not a standards organisation, but they sort of help interpret them. It's a really useful document for those who are installers. It's on their website. They can go to the installer login and download it. And it does have examples of a risk assessment and some of the conditions that you should go through in terms of doing that risk assessment. I'm actually just scrolling through it now while we're talking, and complete one of these as part of every installation. So it's actually a shell. You shall do a risk assessment as part of a battery installation. It probably will become a fairly standardized, a bit like a OH&S process where you've got a standard template that you fill out. So it's a useful document that they've produced. So I'm just looking through here. Andrew, does a hybrid system like the Gen 24 with BYD battery fall under Section 5? Yes, it does, Andrew. Thank you for that question. So just pointing out with my picture over here again, Section 5 system, this would be, in the case of Andrew's question, the BYD battery, and it's a pre-assembled battery system compliant with the best practice guide. It's a lithium-ion battery and it falls in Section 5. What you connect it to on the DC side is a separate issue, and it doesn't actually fall under 5139. So you can connect it to other inverter systems. I've actually got several different inverters I've connected that BYD HVM to, which including Goodwee's new high voltage inverters. They're 3-phase and single phase. So you can actually connect a range of PCE up here with a battery system, and that will still be a Section 5 solution. All right, so sections 4, 5, and 6, that was my little overview. Let's go down to do a case study now. Now, I've kind of prepared it in the sense that I've thought about some products that we could use for these case studies, and I've tried to use very popular products that are fairly typical, and just to look at some of the considerations. So let me just swing over to my drawing pad again. So there was a request before I started this live to do a Section 6 system, and for Offgrid. So that's what I'm going to do first. So this is a section 6, and the reason it's section 6 is that I'm going to be assembling a range of products together. I'm just looking across at my list over here. Gee, it could actually be a section 5, but anyway, we'll cover that. Section 6 off-grid system. So it's going to consist of an inverter, and I'm choosing the very popular Selectronic SP Pro. So here's my SP Pro, and I'm going to connect to it a BYD system. So BYD down here. So now I'm drawing 3 overcurrent protection devices. It's all single pole drawing here at the moment. I haven't done double pole drawing. And down here is my battery. So it's 3 battery modules, and I've decided to use the BYD B-Box. So BYD B-Box. They're 13.8 kilowatt hours each. So it's actually 3 of them, so it's 3 times 13.8 kilowatt hours total. Usable capacity is about 12 point something. These are a 51.2 volt nominal battery module, and this is a 7.5 kilowatt SP Pro 48 volt. Here we go. Now, if anyone who's not familiar with Selectronic will know that this is a battery inverter, not a hybrid inverter, in the sense that it doesn't have any DC from a solar input. It's just got a battery input or battery port, and it's got 2 AC ports, one for grid and one for backup. In an off-grid system, you would typically use that backup port that source port for a generator, for a backup generator. And you would use the other AC port for all your loads. So let's add some solar to this. Where are we going to put the solar? Now, in an off-grid system, you want the solar to work whenever the sun shines. So you're going to have to connect it to, if it's AC coupled, to a reference grid. And the reference grid is actually the SP Pro. So we've got another inverter in this system, and it's a solar inverter over here. And it's got its solar array connected to it. So it's actually connected on the load side of this SP Pro. So this here is a Fronius. We're putting in a Fronius 8.2 Primo. So it's 8.2 kilowatt Primo, but rather importantly, it's what's known as a Selectronic certified, S-Cert for short, Selectronic certified. And this is the SP Pro, the Selectronic battery inverter here. The reason for this S-Cert is that what you've got here is a generation source that knows nothing about the state of charge of this battery system, and therefore there needs to be some command and control system to control the power output of this solar inverter. And in Selectronic mode of operation, their preferred option is what's called managed AC coupling, which means you have a data cable that goes between the two, and that communication cable controls the power output of this Fronius inverter. The loads sit in the middle here, so there's your switchboard with all your circuits. All your loads are down here. The upshot of that is that when the sun is shining, the efficiency is very high in this system because the loads are being fed first. The surplus can flow to the Selectronic inverter, and it can charge the batteries. But let's talk about the battery standard. Now, where does the battery standard apply to all of this? It applies to areas such as right up to the terminals of the PCE, right up to here. This area here is covered by 5139, ASNZS 5139. And one of the things it states is that with parallel strings of batteries, and we've got 3 parallel strings, you need overcurrent protection in each string, and you need to be able to isolate in a readily accessible, within 2 meters of the battery system, each of the battery modules. So let's look at the actual product. Now I've got the data sheets here for it. Let's have a look. So yeah, I've got some data sheets. This is the BYD. It's not a very good picture. It's not a very exciting looking thing. It's a black box, but it's what it does that matters. Inside that black box is a couple of 150 amp fuses in parallel, so 300 amp internal fuse. So internally, there is a 300 amp overcurrent protection by fuse. So there's our fuses here. So we meet the first requirement that I wanted to look at in terms of 5139 is you must have overcurrent protection in each string of a battery system. But there is no isolation device in that box. There's no switch to turn off, or air gap switch that can interrupt the current. There's a semiconductor switch for turning off the BMS, but there's no internal readily accessible switch. So I've had to add those externally. Now, I didn't have to actually add 3 if there was an accessible switch in each one, but there isn't. And so I could parallel those together and have 1 switch, or I could have 3 switches. So I've drawn one option here. If I parallel them all together, the fuses provide the string overcurrent protection requirements that we have in the standard, and the isolation requirements could be those 3 separate isolators, or if we parallel them, a single isolator. If the inverter is more than 2 meters away from the battery system, so there's a 2 meter location requirement, we need to have isolation at the inverter as well. So as long as this distance here is less than or equal to 2 meters, we only need isolation at one end of that cable. But if the inverter is more than 2 meters away, we need an isolation at the inverter end as well. So there's a little bit of detail around the BYD box. Now, I just realized I called this a Section 6 system, but this may well be, because I haven't checked it lately, BYD is probably on the approved list. So it's probably a Section 5. But the only difference would be if this wasn't on the approved list, this would be a Section 6 system. What's the difference then? What in practice difference does it make if this system was on the approved list or wasn't, if it's a Section 6 or a Section 5? It's a location issue. That's the difference. So it means that if you're in Section 5 in a residential installation, you can actually put this system under the roof of a habitable building, basically within a building containing habitable rooms, but not in a habitable room. So it can go in a garage. It can go in a storeroom. But if it's a Section 6 system, it can't go within a building that contains habitable rooms. So that's probably the main difference for going from Section 5 to Section 6 is are you going to be able to put it in the garage? Now, this is an off-grid system, so it's pretty common to have off-grid systems outside of the dwelling, in sheds and outbuildings, so it's not such a big deal. All right, that's case study number 1. I'm just going to check the comments again. I don't seem to have any more in there. I'm really curious, there's no comments on YouTube, so I think I've loaded the wrong page on YouTube. But anyway, apologies to anyone on YouTube who's making comments. I can't see them at the moment, but I certainly will respond to any after this event if I can see them. And I'm just reloading that page. No. So going back to Facebook, have I got any more comments on here? Let's have a look. 21, okay. Oh yeah, there's a few more. And I think I've covered most of them. Wow. I'm really glad I've got Kelly and co there answering the hot water questions for me. Thank you, Kelly. That's really great. And also Bradley answering some of the battery questions. That's great. So let's do our next case study. Our next case study is going to be an on-grid system, and it's going to be definitely a Section 5. So we're doing an on-grid case study. once again, switching over to my drawing panel. So for this system, I'm going to use a solar edge storage inverter. So it's a section 5 because the battery is a LG Chem Resu 10H, which referred to as a high voltage battery. But for those who are familiar with the terminology, high voltage in electrical means greater than 1500 volts DC. But you know what, marketing wins. They say it's high voltage. Oops, section 5 on grid. Here we go, on grid. Glenn, don't talk and write at the same time. There we go. Okay, so section 5 on grid. We are going to draw the grid. And we're going to bring the grid in. We're going to have some loads in the home. So that's our loads here. And we're going to add a storage inverter. Now the storage is a hybrid inverter in the sense that it's got a battery port and it's got the ability to take PV power through what devices known as optimizers, which are little boxes that go on the panels on the roof and make every panel work to its maximum performance independently of every other panel. So it's a great idea. So there's my storage. So storage. The storage comes in a range of sizes. I think it's 3, 5, and 6 kilowatts. So let's say we're putting in the SC6000, which is the 6 kilowatt unit. AUS for Australia. We're also adding a battery system to this, and this battery system is an LG Chem Resu 10H. So LG Chem the naming refers to the capacity. It's got a total capacity of 9.8 kilowatt hours. Now, what I've drawn here is a point of isolation of the battery system. It's a requirement of 5139. As with that off-grid system we looked at, to be able to isolate the battery system within 2 meters of the power conditioning equipment, which in this case is the storage. So you might ask, well, and it's come up quite a few times recently in my courses, this particular battery has an inbuilt circuit breaker that is technically readily accessible. That means you can operate it without a tool, but it's almost requires a little bit of customer training how to open the door. It's around the back. It's got a double action latch. You've got to do a lift and pull in the right order to open that little hatch to get to the circuit breaker. So it is technically readily accessible, but you know, if you think about the intent, is if something's going wrong, someone can quickly turn it off and they don't have to read a manual on how to open the door. So in practice, most people are putting an external isolation point external to the battery unit. But, you know, if you can convince your inspector that you've trained the customer and they can actually open that door in a hurry, maybe it's okay. I haven't drawn isolation on the PV side. I've just been focusing a bit on the battery. Why is it a Section 5, by the way? It's a Section 5 system because LG Chem's Resu 10 is a pre-assembled battery system and is on the CC approved list. It's got best practice guide compliance. So it can fall into Section 5. It's not integrated with the inverter. The inverter is a separate product from a separate company. So this particular battery can be used with a range of inverters. So with SMA, for instance, also with Huawei, and probably others. And the storage works very nicely with this unit. So I've got this set up actually in the lab here, just as I've drawn it. But I'm missing one thing in this drawing that's really critical. It's the energy meter, I just realized. So you still need that energy meter, and it comes with the storage, so don't worry about it. And it's a solar edge energy meter. It's quite a big unit actually, and it's quite sophisticated, but it does take up a bit of room. So you have to plan for, I think, about 11 poles of room and a switchboard for it, or put a separate enclosure. But that energy meter can be connected through the inverter to the cloud. And so it gives you a lot of monitoring as well. So the energy meter, once again, communicates the energy flow at the point of connection with the grid. and therefore can allow this system to see which direction the energy is flowing and choose whether to charge or discharge to support the loads or to charge surplus solar. So there's your section 5 option. All right, so looking back at questions again. Okay. I keep having to reload the page for some reason. It's a bit of a pain. So see your questions, sorry. Here we go. And I can't see any new ones. All right. Okay, good. All right, so that's the two case studies I wanted to cover. And the last point I want to cover today, because we've been going for an hour now, is basically location, location, location. I've talked about a lot of this in my training, the issues associated with finding a suitable location for a battery energy storage system, particularly in a residential location, because of the issues associated with clearances that are required for battery systems. Now, I'm going to once again do some drawings. That's kind of what I'm here for today, is to draw things and explain things. Let's look at some of those location restrictions. Now, they do relate to which section you're in, but there's some which across all of these sections. The big one is if you put a battery system on a wall that is adjacent to a habitable room, and if you're allowed to, so that might rule out Section 6 systems, but a Section 4 and 5 can be installed in a building that contains habitable rooms. But if on the other side there is a habitable room, and those are defined in the building code, the National Construction Code, but include things like bedrooms, lounge, kitchens, bathrooms. So they're all habitable rooms. But if it's a hallway, a utility room, a storeroom, a garage, it's not a habitable room. So a garage is a very popular place to install a battery system. So let's do a plan view of a garage and work out where we can put a battery system and what protection against the spread of fire may be required. So I'll just move over to my drawing. Okay, here we are. Plan view of a house, real simple. Here we go. There's the house, and this is the garage here. It's the entrance to the garage, and there's a little bit of a brick wall like this. Goes back, and goes back to here somewhere, and there's a door. Probably swings that way. There we go. So there's our house. There's our garage. And we're going to put a Section 4 or Section 5 system. Now, first we need to know what's on the other side of these walls. So let's say here is the lounge. So it's definitely a habitable room. So we've got a lounge on this side. Here is a hallway. And it's just supplied by that door. So probably some other rooms elsewhere. Okay, so let's look where we're going to put this battery system, and I'll draw the battery in red. Can we put it here? Question: yes, we can. We can put a Section 4 and a Section 5 battery adjacent to a wall that has a habitable room behind it. But, and there's a couple of buts, is that wall now has to have a barrier for the protection against the spread of fire. And the barrier needs to extend 600 either side and 900 above. So just in plan view, if I just draw that over the side here, if my battery system is this big, that's my battery system, or BESS, so it could be a BESS or a battery system. I have this requirement to have 600 and 900 above. Protection against the spread of fire. So that's 900 and that's 600 here. And that fire barrier, it's not actually called a fire barrier, it's called a barrier for the protection against the spread of fire, can be made of brick, concrete block, terracotta tile, cement sheet, or a material rated to AS 1530.1, which is a non-combustibility rating. So that area around here is the fire barrier that would be required. So I better draw that in there. So I'm going to put the fire barrier in. So here's our fire barrier behind the battery system and above it. And if the ceiling is closer than 900, we also have to line the ceiling or the eave if it's outdoors. So that's a location that we could do. It's going to be a bit more expensive because of the fire barrier, but we've got another big problem. And this is when, if you were in the classroom with me, I'd say, what about the car? If you've got a vehicle entering into this space, now this has nothing to do with the battery standard, by the way. This is more to do with AS3000 in terms of mechanical protection. There's our vehicle entering, there's our bonnet, headlights, whatever. It could easily bash into that battery system. So mechanical protection requirements would probably be a guaranteed requirement here. So you'd have something like bollards. So you might have some bollards in front of that system. And if that has doors on it, you're going to have bollards that you can remove for maintenance purposes, or some are hinged to get access to that. So this is probably not the best location because of the extra cost to the fire barrier and the bollards. But what about by the door? Well, we could put it by the door, but we've got to be 600 mils away from an entrance. So if we put it here, as long as we're more than 600 from the opening, so if that area there is greater than or equal to 600 mils, then we're good. We probably still need a bollard because the vehicle could slice it sideways, so we probably still need bollards there, but we don't need the fire barrier because there's no habitable room on the other side of that wall. Ditto on this side as well. So really, we've got a few locations within this room that we could put a section 5 or section 6 battery. So I better write that there. Section 5, 4 or 5. Section 4 or 5 battery. So there you go. Now we're nearly finished for today. I just realised my peak covers a little bit of my drawing. Sorry about that. And I'm just checking one more time the comments coming in, see how we're going. And looks like there was a rash of comments and they've slowed down, which is great. So I think I've covered most of those. Anyway, so thanks very much, everyone, for attending today's Toolbox Tech Talk. I'm doing them every Sunday at this time at 2 o'clock every day. And I just better bring myself back on. There we go. So yeah, 2 o'clock not every day, 2 o'clock every Sunday for about an hour or so. I usually interview someone, or sometimes I just do a solo event and just cover some particular area that's relevant to our industry. I've had some great guests on this show before, and there's more coming along. So you can look forward to those. I'll announce them in the week coming. But just one more plug for my course that I'll be running on the 5th to the 9th of October. It's a 5 half-day course. It's 5 half-days in a row, Monday to Friday, 8 a.m. to 12:30 p.m. With a little morning tea break thrown in. It's run on Zoom. So you're in a meeting in Zoom with me and about half a dozen to a dozen other students. So I keep it as a small group, a dozen roughly, and we do a full system design and standards assessment for a solar and battery system, both on-grid and off-grid. So that's something that's coming up next week, the 5th to the 9th of October. You can register for that course on YouTube. You'll find the link for it in the comments beneath my live stream. It's also available on my website, solarquip.com. So you go to solarquip.com and you'll find the registration. So that's it for me today. Thanks everyone for attending, and see you next week. Okay, I'm out.